Okay, in this section we're going to be going through magnetism, and we're also going to be talking about the electromagnetic spectrum. So we're going to start here, 9C, with magnetism and then magnetic fields. So a magnet is, in the physics sense, a magnet is an object that produces a magnetic field. So that's the technical definition of a magnet, something that produces a magnetic field. Magnets, the reason they exist, it's because their atoms align with each other. So if you have enough atoms in a magnet, if enough of them line up together, you're going to get each of their mini magnetic fields lining together, and that's where magnets technically come from. It's basically what's happening at the atomic level. So some common magnetic materials include steel, cobalt, and steel, nickel, cobalt, iron. So nickel, cobalt, iron are all elements, and then steel is actually a compound of usually iron and carbon. So those are common magnetic materials. So magnetic materials are very similar, or not magnetic materials. Magnetic fields are very similar to electric fields, and there's one right here. So this is what a magnetic field would look like. So again, it's kind of similar in terms of, there's arrows, there's the lines indicating where the field is. But instead of positive and negative charge, magnets have poles, basically, a north pole and a south pole. So again, with electricity, electric charge, you had positive, negative. Magnets are going to have a north pole, a south pole, like right down here. You see there's a north, there's a south over here. And you're going to have basically a very kind of similar interaction to electric charges. So again, with electric charges, if you had a positive and negative like this right here, they would attract. So opposites attract. It's the same thing with magnetism. If you have a north and a south pole, and then you have another magnet over here, and its north is over here. If you have opposite magnetic poles, they attract just like basically the electric charge, and then if you have the same magnetic poles, they're going to repel each other. So in that way, yeah, magnetic poles, basically electric charge, are very similar. And magnetic field lines, just like the electric field lines, they have arrows with them. You can see them like right here. So the arrows are going to point away from the North Pole, like right down here. They point away from the North Pole, and they're going to point towards the South Pole. So if you look at it closely, you'll see all the arrows are pointing towards the South Pole. And that magnetic force is going to get stronger near a magnetic pole. So if you're out here, if you're a magnetically charged object, you're going to experience more force if you're closer, and then even more if you're really close to one of the north or south poles, right? Where you see all the lines get dense, there's more of them close together. That's where there's going to be a stronger magnetic force. And also, like electric fields, magnetic fields, you can store energy with them. So what you're going to get is you're going to see that there's magnetic potential. I want to write it up here because it's a little cramped. Energy. So again, just like there was electric potential energy, there's magnetic potential energy, and that magnetic potential energy is going to increase when the poles, when you have like poles close together or opposite poles further apart. So if you have, sketch it quick, if you have two south poles close together, if you do that, if you bring them together, they don't want to be near each other. So if you do that, you're storing more and more energy, basically. They're going to fly apart more violently when you let them go. So you're increasing the potential energy if you bring like poles together. It's the same thing if you take unlike poles and you pull them further apart, like this down here. If you pull the south and the north right there lined up, you pull them apart, you're actually increasing the potential energy in that way too. So it's kind of the opposite. So like poles, if you push them together, you increase the energy. Unlike poles, if you pull them further apart, you're increasing the energy. And the last thing to note is that you can't have a single magnetic pole. It's not like charges where you could just have a single positive or a single negative. The magnets have to have both poles. So it's not like electric charge. So you always need to have a north. You always need to have a south. If you were to somehow take a magnet, well, not somehow, you could do this, and just split it into two smaller magnets, what you would get is just they would both have both a north and a south pole. So you can never just have a north or a south pole. You need both. So that's basically magnetism. There's magnetic fields. They're in a lot of ways they're similar to electric fields, but you have to be careful that you realize that the north and south pole are inseparable, unlike the positive and negative in electric fields, electric charges. So we're going to move on to the next section. So the next section, where is it? Okay. So the next section is the electromagnetic spectrum of light, or the EM spectrum, EM electromagnetic. So light, what it really is, it's a combination of an electric field and a magnetic field oscillating back and forth. Oscillating mean like interacting with each other in a repeated way. So this is kind of what it looks like. So let's say you have an electric field, E for electric field, and then I'll do this in a different color. Sure, this color. Come on. Okay, so let's say you have, and then you have the oscillating electric field, and then what's happening is there's also an oscillating magnetic field that's kind of right along with it, and it's those two fields interacting with each other, vibrating kind of back and forth. That's technically what light is. So this would be a magnetic field. So again, kind of interesting, but that's what light actually is. Okay. Sorry, 1 second. There we go. Okay, and light, that's why light in a scientific sense is often called electromagnetic radiation, because it really is made up of an electric element, a magnetic element. And all types of electromagnetic radiation are going to move at 3.3 times 10 to the 8th meters per second, right? Speed of light. But it's important to note that visible light, what we can see, is only a small part of the electromagnetic spectrum. Electromagnetic spectrum. And that spectrum's kind of below right here. So all of these are different types of electromagnetic radiation. Visible light's only one of them right here. So there's actually 7 different types of electromagnetic radiation, and they're listed below from the largest wavelength to the shortest. So the largest wavelength is radio waves. They're pretty large wavelength. And then the shortest is down here. We're going to say what that is in a second, but its wavelength is really short. So again, they're listed as you go down this table, right? As you go down this table, the wavelength is going to decrease, the frequency is going to increase, the amount of energy, right, that is lowercase e, I guess, would increase as well. So again, they're listed from, as we go down, you're going to see the wavelength go down, the frequency go up, the energy go up. So we're going to go through each one. So radio waves, those are mostly used in telecommunications. Their wavelength is about the size of a football field. It's pretty big. Microwaves are used in communications and cooking, so microwave oven. Their wavelength is about the size of a bumblebee. Infrared light, that's used for sending short distance signals like remote controls are usually infrared. And heating, wavelength is about the size of a cell. Visible light, that's what we normally see. That's how we see stuff, is with visible light. The wavelength is about the size of bacteria. The next one is ultraviolet light. Ultraviolet light, and that's used in sanitizing materials and tanning beds. The wavelength is about the size of a virus, so really small. X-rays are used in security and taking images of bones. The wavelength is even smaller, it's about the size of an atom. And the last one, gamma rays. Gamma rays are mostly used for research, and they're technically a type of radioactivity, and we'll get into exactly what that is later. And their wavelength is really small. It's about the size of not even an atom, but just the atom's nucleus. So that's the spectrum. Again, it's made up of lots of different types of radiation, but they all move at the speed of light, and they're all made up of oscillating electric magnetic fields. Okay, last thing, we'll do a problem. Where are we? Here we go. So again, make sure you take a second to do it before I do it out. Right, you're doing it, you're not playing words with friends. Okay. So we have a circuit that's built using two small magnets to receive a specific radio signal. Okay, so that's the idea. Some circuit, there's magnets in it, and it's receiving a radio signal. Saying sketch the magnetic field of one of the small magnet, should be plural magnets. So again, a magnet, let's just assume it's a bar magnet. It's going to have a north pole, south pole definitely, and then the magnetic field, you're going to have field lines that go from the north to the south, like this. Just draw a couple of them. And then to be perfectly specific, we want to put little arrows coming out of the north, going into the south. So that's what the magnetic field would look like. All of the lines have to be complete from north to south. That's what it would look like. That's what the magnetic field would look like. B, if you move the north poles closer together, would this increase or decrease the amount of magnetic potential energy? So we're taking, if we took the two small magnets, and let's just assume they're bar magnets, or rectangles, if you took the north poles and moved them closer to each other, what would happen with that to the potential energy? So if you're increasing them, if you're pushing them together, the north poles don't want to be near each other. They want to repel just like two negative electric charges. So if you do that, the potential energy would actually increase. So increase. And the last one, do the radio waves received have a higher frequency than microwaves, a higher energy than microwaves? So if we look at the table, if you flip back to the table in your notes, it actually, do they have a higher frequency? No, they actually have a lower frequency. Radio waves have the lowest frequency out of anything, any of the types. And no, it's going to actually have a lower energy. So again, radio waves has the lowest frequency, it has the lowest energy, so it's going to be no to both of those. Okay, that's about it. So that's kind of an example with some of the concepts of magnetism about the electromagnetic spectrum. So make sure you have this copied down, and that's it for now.